relevant in the 1990s. So then, as he updated the material for newer editions, he came up with a new architecture. And that new architecture is called the MMIX.
Okay,
But
so
yeah,
so basically he came up with a second architecture that's not going to be commercially used, basically.
yeah. So it hasn't been manufactured so far, and there have been, some low-level implementations, like in terms of the design, like the microarchitecture. But yeah, I don't think anybody's actually ever physically, manufactured or even prototype a computer. But there's no reason why you couldn't do it. I think that, if you have access to the materials, like at some maker lab or something like that, it's to me, it seems not inconceivable that you could do that. Um, and there's been developments more recently in the hardware world. There's this open source architecture called RISC-V, and that has picked up a lot of popularity, and it's really opened up the space for doing your own designs, computer designs. So who knows? Maybe somebody may find the motivation to do this. Yeah.
Sounds very interesting. I think in that case, I'll also take 1 or 2 minutes to get ready.
Sure.
While people come in.
Okay.
How do I can turn off sound and video, right?
Yeah, you should have the mic and the camera icons on your Meet. Yeah.
Cool. Okay. See you in a bit.
Okay.
Are we waiting for Arthur or Michael or?
Well, let's see. I think Arthur did confirm. Yeah, so Arthur said yes, he would attend, and then James also said, I haven't seen Michael's RSVP, so, but he does often just RSVP just before the meeting, so you never really know.
Right.
In any case, we can wait another minute or two.
Sounds good.
Start. Yeah. Hi, Michael.
Hello.
How's it going?
Going fine.
We were just talking about you, how we didn't see your RSVP, but I said you're often like, you just RSVP before the meeting, so we never really know.
The RSVP does not work for me for some reason.
Oh, wow.
It just gives me a gray screen. It works half the time. I don't know what the deal is. Oops. Is my camera on? No, it's not, is it?
Your camera is off, but yeah, we can hear you.
There we go.
Yeah. See you.
So it's kind of weird. I mean, I figured out how to do it so it doesn't happen very often. I remember early on, one of the earlier meetings, I just couldn't get in.
Yeah, I do remember that. And I think that I noticed that you had 2 accounts. You had 2 Meetup accounts, and then I saw,
I have 2 Meetup accounts? Really?
Yeah, so I think I saw, your name twice on the RSVP list, and I noticed that. So that you may want to look into that.
Meetup, we think I have 2 accounts, but I only have 1 name on there.
Okay. All right. Well, we have a new attendee today. Adam joined us. So Adam, if you don't mind telling us where you're connecting from.
Yeah, I live in Nice, France.
Oh, wow.
So quite a bit away from, well, where are you guys actually?
So I'm in New York City.
We're all pretty close to New York City.
Oh, okay. Yeah. So I guess I'm taking advantage of the fact that everything is going online, huh?
That's wonderful. That was really one of my goals was to schedule it at a time that could work for people in Europe. We've had a couple of people connect before, but not recently. Yeah. Very nice.
Cool. Yeah, so you are open to it.
Oh yeah, absolutely. No, we're definitely open to it, and that's great. I mean, if it works out for you, then that would be wonderful.
Yeah.
All right, cool. I think let's get going. So here is today's agenda. We're in volume 1, and it'll be section 232, which talks about the binary tree representation of trees. So in one of the earlier sections, I think the sections, 2 sections before, Knuth introduced the concept of a tree, the data structures, and then he distinguishes between just trees and binary trees. And with trees, he also introduced the concept of forests, which are these disconnected trees. And so over here, we'll see a way that we can relate any arbitrary tree or forest to a binary tree representation. And then there's an application that's being discussed, which is to compute the derivative of an algebraic expression. And then there's some code to go along with that. And we'll also try to do some exercises. So we generally go for about like 50 minutes or so till 3 o'clock. And then we'll take a 10-minute break and just come back and continue till 4. So here's the scheme that we've been following. We'll read a few pages, just enough for about 5 minutes worth of reading on average. Sometimes we'll allocate like 7 minutes if there's a little more material or it's a little more complicated. And there'll be a slide that I'll share that'll show us exactly what we're supposed to be reading. And then when we're done reading, then we start the discussion. There's no time limit on the discussion, just however long you want to take. And while we're reading, it's great if, you know, anything that comes to mind, you just type it into the chat. I do keep a record of the chat, and it gets posted to the GitHub repo. And the video is also recorded and posted to YouTube. So, again, volume 1, chapter 2, and let's start with page 334 through 337. We'll spend about 7 minutes on this. The last line on the slide shows what's the snippet of text on page 337 that we're reading up to.
Okay.
I'm sorry, but I'm just having problem finding where to start. Can you say like the first paragraph or section?
Oh, so this is the beginning of the section.
2.3.2. Yeah, mine begins with different words too.
Yeah, I didn't put the beginning snippet. I just put the end.
Mine goes, we turn now from binary trees to just plain trees. That's the first sentence.
Yeah, that's the first sentence.
3.2.
Oh,
Yeah,
mine
I apologize. The
344.
the
Yeah.
the
Sorry, go
snippet
ahead,
is for the end of the reading. I didn't put a snippet for
We
the
start
beginning.
with page 344, right?
334 in the third edition.
Oh, 34, my bad. Oh, I have the first. Oh, okay. Well, I guess I'm going to have some addition problems, but I guess we can take care of that later.
Section 2.3.2 should be pretty much the
Okay,
same.
got it. Okay, thanks.
Do we need another minute or two?
I think I can't see the slide where you put the where we finish.
You don't see a slide at all?
Yeah, I don't see slides on my phone.
Okay. Wondering if it's a layout choice in your settings, maybe?
I see that there's 3 of you in the call. Is that like one of them is a slide?
There should actually be 6 people in the call.
Yeah. Oh, I meant like 3 of you.
Oh, 3 copies of me. Yeah, that's
Yeah,
right.
exactly.
That's right.
Both sentences are correct, I guess.
Yeah, yeah. Yeah, there's probably some, I don't remember trying it. Let me check my phone, actually. I can try to see it on my phone.
You read until the next paragraph starts talking about algebraic expressions. The last words are what? 337.
Can you read the beginning of that paragraph?
No, it's through the first paragraph on page 337, but again, the page numbers are going to be different for you. So we're going to read till the beginning of where he starts to apply these methods to algebraic formula representations. So there's, at least in my edition, there is a figure that has an equal sign in between that shows a binary tree on the left.
Yeah,
it shows an algebraic expression.
Okay.
It shows an expression, and we're not reading that paragraph. We're reading right up to that paragraph, but not that paragraph.
Okay, I got it. So I'll take a few more minutes to read up to there.
So it says, the paragraph ends with, because of this equivalence, we use notation $P. Love that. For the post-order successor of node P in a tree, while it denotes the in-order successor in a binary tree.
Yep. Okay, got it. Thanks.
Okay, while Adam finishes up, can we, let me,
You cut off your audio, Zakesh. No. Now you have 2 audios.
Okay, how is it now?
Echo.
Let me just disconnect from my phone. I was just trying out what I would see on the phone, and it does show me the slide as the main thing on the phone, and then it has little tiles on the bottom for each of the people. Is that not what you see, Adam?
No, unfortunately. So I did see the slide when I joined the group, but now I only see the 3 participants, the 4 of us.
Okay. I have a feeling that it somehow switched your layout, so you may want to look at that, but the slide is visible, at least on my phone. Welcome, Gabriel. Can you hear us? You're muted, by the way.
Hello.
How are you?
Fine. I tried joining a few times. Now I finally managed.
Okay, very nice. What happened earlier?
No, it's just that I'm in Europe, so it's late already. So it depends on. Well, last time I fell asleep before joining, so.
Oh, I thought you had some connectivity problems, so that's fine.
No.
Yeah.
It's just that I tried joining this meeting like a few weeks ago already, and yeah, it's just that I'm in Europe, so it's night, so that's the only reason why.
I understand. Where are you connecting from in Europe?
Now I'm in Zurich.
Okay, cool. So we have I'm in New York City, by the way, and we have Adam who's in Nice, France.
Okay.
Miguel who's in Brooklyn, and Michael who's in New Jersey. So welcome. We just finished reading the first section, and I've shown the page numbers that we just read. So if you have access to volume 1 of the text, that's where the page numbers are referring to. Is that what you're reading right now or looking at?
Yes, but I will check. I'm not sure I have it right now, but it's okay. I will find it.
Okay, cool. So yeah, so we just finished reading about this correspondence or creating an equivalence between a tree or a forest of trees and a binary tree. So how do you represent arbitrary trees that may have many child nodes using a binary tree which can have up to 2 children per node? So could somebody explain how that equivalence or the correspondence works?
Can I give it a try?
Thank you.
So basically what he says is you take any tree and the process is connect all the siblings. He says all the same, the nodes of the same family, but I think he means siblings. All the nodes that have the same parent. Connect them together, like make an arrow to each of them, and remove all their ages from the parent, and only leave one of them, the leftmost, I guess. And with that, you end up with a binary tree that only have that the root only have a left node, doesn't have a right one. So what that means is you can construct it back. You can recreate the old graph from this, right? Because it's if it has an edge, then if it has if the parent count, if you are left, anyway, you can be reconstructed. Let's not go through there. And yeah, then he continues to say that if this happens to be a threaded tree, the newly constructed binary tree, then the rightmost thread always points to the original parent in the original tree. Right? I think so. Something like that, yes.
Okay, any other comments or?
Yeah, I have a question.
Yeah.
Actually, that's entirely how I understood that it works, but I think you said that once you transform it into a binary tree, you can't go back to the original forest representation. Is that what you said?
Yeah, I think it's only when it's if you make it threaded. I'm not sure now.
When I read it, I was under the impression that it's a one-to-one correspondence. So you get an application and its inverse to go back.
Yeah, exactly.
I agree with Adam. You can go backwards and forwards. It's a two-way.
It's a two-way, right? Yeah.
Two-way. So
yeah, the threads, I guess, just makes it easier because you have the extra connection, so you don't have to do the whole algorithm. But yeah.
Right. Right.
Could
Right.
you?
So the right link, the
go
right
ahead.
links, the right links on the tree will point to siblings, and the left links will point to the first child.
Yeah, exactly.
And
Yeah.
what was a little bit new for me, I've seen that done to a tree, but this can be done to a forest.
Yeah.
First level, if the first level, instead of pointing to siblings, it points to the right links point to other trees in the forest.
Yeah,
So A
from
pointing to D, they're not linked in the original. In diagram 1, A and D aren't even linked. They're different trees, but A points to D, and if you had another tree in that forest, then D would point to that. There's no reason why A has to point to D or D has to point to A because it's a forest. There's nothing said about that. But on this representation, the top one would be if you follow the right links, you get all of the trees in your forest. So you can see the forest for the trees. Okay.
You can see the forest for the binary trees. Any other questions? Could
So
someone
just if
explain
I,
the threaded links in that binary tree that is constructed?
So it's the same threading that we did last week. It's on the child nodes. Any node that would not have a left link has a left thread instead, and any node that would not have a right link, that's because it's on the bottom or near the bottom of the tree, would have a right link instead, and the right link goes to it's the in-order successor or the in-order predecessor, right?
Well, that's in the case of a binary tree, but he
it is a
relates
binary.
it to the original tree.
Right. If when it relates to the original tree, he's saying it's post order becomes in order, right?
Yes, so that's the whole traversal, but in terms of the actual node that it's pointing to.
I think you mean that the rightmost node, the right thread of the rightmost node points to the parents of its siblings in the original graph, the original tree.
Yeah, I think that it's slightly different from what you said, but it has most of the same elements. What I'm seeing on the bottom of my page 335 depends on your edition. He says, notice that right thread links go from the rightmost child of a family to the parent.
Yeah, so literally what I said.
Is that what you said? Parent of, oh, okay. So parent of, yeah, I guess it's the same parent. Right. But he also points out that left thread links don't have such a natural interpretation. Going back to Michael's comment on the relationship between a post-order traversal of the binary tree actually being an in-order traversal of the original tree or the forest of trees, could somebody apply that to the example that we have? So in figure 1, we have that forest of 2 trees. And then in figure 3, there's the binary tree. So are you able to see that if we do a post-order traversal of figure 3, we are getting an in-order traversal of figure 1? And if somebody sees that, could they explain it? Or just maybe walk us through that traversal?
Right, let's give it a try.
Okay.
So it's saying there is no analog to the in-order sequence, since there is no obvious place to insert. Actually, this actually confused me when I read it. I jumped straight to, okay, forget it, the comparisons between in-order and post-order. What is the pre-order? You traverse like this way, and that's it. But let's read it anyway. So there is no simpler analog to in-order sequence, since there is no obvious place to insert a root among its descendants. So that sentence, I don't understand it. But pre-order and post-order carry over the obvious manner. Let's go back to what pre-order and post-order. I guess some of you had this at school, but I didn't. Where are you?
So I've typed in the chat what I would like us to understand.
Right, so in-order traversal is traverse the left subtree, then visit the root, then go to the right. So the pre-order here, so you start on the root, go to the left, finish the left all to the end. Then, so if we imagine a bigger tree, we will start on the root of the big tree, go all the way to the last left, right? Go up to its root. Then
I'm sorry,
right.
Miguel, I have this opposite. So actually it's the in-order traversal of the binary tree, because in-order of an arbitrary tree doesn't actually make sense. That's the point that I think, Miguel, you were asking about.
I see.
Right, because for in-order you have to say there's some child that comes before the current node, and then there's some other child that comes after. But if it's not a binary tree, then how do you decide where the current node is going to be placed between all of its children? You'd have to pick some arbitrary
right. You have to
location.
pick a children.
So that's what he means, that in order for an arbitrary tree doesn't make sense, but in order for a binary tree makes perfect sense. And for the binary tree, in order, it corresponds to the post order of the
right. Traversal the first tree, which is the left, right?
Yeah.
And then the root, and then the remaining. Yeah. But so what it says, actually, let's stay there for half a second. When it says traverse the subtrees of the first tree, so imagine the binary tree. You are in the root, in the top root. Then step on into your left. That's the first one, right? Then you should continue to the left, right? Go again to the left, and until there is no more left, until you are. Is that it, right? And that's when you are actually, and then go back to, so the question that the part I don't remember is after you reach the last left, you then go to, well, you have to go back to the root you were before, right? So that's the question. You go all the way to the original root, or just to your own root, to the root of the smaller.
Just to the parent. Just to the parent.
And then the last left, right? And then go to the right. And then
you're going to go to the right. And then if that has any lefts, you're going to follow all the lefts all the way down.
All the lefts, right? Yeah. And then you go back to the root when you visit the whole subtree and go to the next right and the next, and so on.
Yeah.
Got it.
Okay, so could somebody type in the in-order traversal of the binary tree in 3? Can you just type in what that result will be?
What do you mean 3? In 1?
No, the binary tree is in 3.
Oh, I'm looking at the wrong page. Sorry. No, never mind.
On page, yeah.
Yeah. See, so we'll be typing.
Can't find my chat window. Where's chat? Oh, here we go.
Okay, so Adams typed in what is supposed to be the in-order traversal of the binary tree in figure 3. Is that correct?
BKC, A, H, E, J, F, G, D. Yeah, that's what I got.
Okay, so that looks good. Now, can we relate this to a post-order traversal of the forest of trees in 1? We don't have to, I mean, obviously it should turn out to be the same, but is it clear that this will be a post-order traversal of the 2 trees in figure 1?
So I have a question.
Yeah, go ahead.
Is it helpful to imagine that the forest has an extra root at the top, which has all the other roots of the trees as its children? So basically to connect the independent trees by a node up above.
So I think you bring up a good point, and I noticed that, let's see, below the binary tree shown in figure 3, the paragraph that begins, the transformation from 1 to 3 is extremely important.
Yeah. So
At the end
why
of
is
that,
why is it necessary to have a root?
I just wanted to point out that in that paragraph, Knuth says we might also change our viewpoint slightly and let the root of a tree correspond to the list head of a binary tree, thus obtaining a one-to-one correspondence between trees with n plus 1 nodes and binary trees with n nodes. Is that kind of like what you're suggesting, Adam?
Yes, I think that is. That's what I understand.
So that's the problem that I have, is that my answer is also, it sounds kind of like that, but I wasn't sure. So,
okay.
So I'm asking the question.
Yeah.
Well, we'd have to understand what your question is exactly.
So if you were to add a root at you have a forest and you're going to put a root node at the top, it doesn't add very much. When you use this algorithm to transform your enhanced forest that has this root, where does that root go? It's going to be, the first node in this transformed binary tree is going to be a root. The root element has no siblings, so it's going to have no right branches, no right children. And the left child is going to be the first tree. So all you're doing is adding a root node straight up the top of that list. Why?
Yeah, I agree with you totally. But what you call, what did you say? An expanded for
the threaded tree?
Transformed?
Yeah, transformed forest, I call a tree. I mean, the idea was not to make it simpler for the binary tree transformation. The idea was just to generalize forests into trees. So for example, I've never had to do any order traversal on forests before, but I did do it on trees at some point in my life.
Yeah.
So I just remarked that if you add, you can basically have a one-to-one correspondence also between trees and forests, kind of, if it makes sense. So,
yeah, okay. Good enough.
I think that's fair, but I would agree with Michael that it actually, I would actually go a little further. Not only does it not buy you a lot, it actually takes away a little bit, because a forest is a more general thing, right? So you're sort of constraining forests to become trees. You're constraining them to become connected somehow, but you're not gaining much in terms of computability or ease of applying algorithms. Whereas here, because he's giving you a transformation or correspondence mechanism between forests and binary trees, that means that when you're faced with a problem of disconnected trees, you can now start using binary tree algorithms on them. Whereas, if like it's just some generic tree now, but it's still a generic tree. You haven't gained in terms of limiting the number of children per node or knowing certain properties of binary trees, so that would be my answer.
Oh, yeah, I totally agree. It was just in my mind to view forests as trees to apply what I know about trees. But yeah, I absolutely agree with both of you. Yeah.
Okay, let us continue. And again, all these page numbers are the third edition of volume 1. So we will continue on page 337, and the 2 lines at the bottom of the slide are the snippets of the beginning of the reading and the end of the reading. But essentially, we're going to look at this little piece where he explains how a tree could represent an algebraic formula. So it's not a lot of text, just a little bit. Okay, who can explain how a tree can represent an algebraic formula and what is the particular benefit of this binary tree correspondence in that case?
I could try to give some kind of explanation.
Thanks, Adam.
I'm going to try not to go too philosophical, but basically by assuming that in math we start with constants, like elements in a set, like the numbers, and we have operations defined on them, which may take any number of elements and return one element, basically. If that's how you define doing calculation, then this is analogous to having a tree structure where each node can either represent an operation or be a terminal node, which then represents an element. And by viewing operations as in a function mindset, you can basically recursively define any formula. And then you asked what is the significance of the binary trees. So do you mean the right tree where he does the transformation?
Yeah. Why is he introducing that binary tree?
So I think what I got from reading this is that the tree that we construct from the formula could be a general tree. It could have any number of children in node. And I don't know if this was related just to the fact that functions exist that take more than two elements, right? Like we have functions from n-dimensional spaces. So if you have just a general tree for the calculation, you can make it into a binary tree, which is interesting to us because, I don't know.
Anyone have any thoughts on this?
Maybe the traversal.
The tree on the left is transformed in the same way we transformed the generalized tree to a binary tree. So the links are going to be following in post order. I mean, that's what they're setting up, post order. And if you do it that way, then it's easier to evaluate. It's easier for a computer to evaluate the expression.
Is that because it's related to the postfix notation?
Yeah, I guess it must be. Yeah, sure.
Yeah, that's the takeaway that I had from that section, is that, postfix, if you're familiar with that notation for evaluating and representing algebraic expressions, it has a lot of benefits in terms of computation, because you can use like a stack for that, right? And the fact that we are now able to get this binary tree representation of the original formula tree, and have this knowledge that the in-order traversal of the binary tree will give us a post-order traversal of the original tree. I think that's where this is sort of going. Sound good? Any other questions or comments, thoughts?
I have a question.
Yes.
With the addition on the right of this y at the very top of the tree, so it is the same y as in the formula on the other side of the equality. But then the equality symbol is omitted. So basically, is it because we can still differentiate between the left and right hand side of the expression? Or is there a reason why this equality symbol is omitted?
Well, equality isn't an operation. It doesn't do anything. I mean, you think of equals in a language like Fortran or Java or something like that as an operation that assigns the right-hand side to the left-hand side, but it doesn't even mean that. It just means that the two sides are equal. So the only thing that could come above it would be a single variable. So he does that in a lot of these representations. He puts in an element that has a link to itself, like that y does, and he calls it the head of a list.
But so my question is this head of the list connected with the let's say the two terms of this expression, basically, or is it just for adding a head?
I think it's just there.
So the way I'm seeing it is that the arbitrary tree, the generic tree representation, is for an algebraic expression. It's not for an equation. So, you can do either the left-hand side or you can do the right-hand side and you get a tree. Or you may think of it as maybe two trees or whatever. But with the binary tree, it's giving us that ability to say that there's one node where we can somehow say that this is the resolved tree, so he's able to now represent that left-hand side y in the equation as that, root resolution node, which we can't really do in the generic tree representation, that easily at least. That's my interpretation.
Okay, and now, for example, if we were to have y minus 1 instead of just y, how would we insert this in this representation? Then it would be on the right of y, then you would have this plus or minus and 1 that would be added, I guess.
Yeah, I think the idea would be that, you would take everything over to one side, and then whatever is left over, that's going to be your, result,
yes. So you would take the whole expression on both sides of the equality as two trees, forming a kind of forest, and then you connect them together via this transformation.
That's a good question, but the way I'm seeing it, I would just add 1 to both sides and just leave y on the left-hand side, and then just apply this transformation to that.
I don't think this is going there. I mean, you could have something like, instead of y, you could have y squared equals that whole function, or y, y plus 5 equals that whole expression. He's not going there. All he's doing is he wants to differentiate that expression dy dx, I guess. I mean,
correct me if I'm wrong.
I don't think that head of the list adds anything except maybe to describe the algorithm in terms of a list.
I think what it adds is the ability to say that we have a result at some point, that, that the value of y of that extra new node, that's the answer. That to me is.
But you had a top node in the left. You had a node at the top. that was where your answer went. Why do you need why? You
but
don't
on
need
the left, it's not the computation tree. It's just the formula, the general tree. But I agree. I think that the nodes can the links between nodes can play a declarative function. So when you have a node with just a variable name and under it you have a subtree, then it's as if you give a declaration for a variable. That variable takes the value calculated by the subtree, which I think basically is what you were saying.
Yeah. Okay.
Sorry if I'm mispronouncing.
Yeah, I that's my sense. Again, that this right tree is exactly what Adam said. It's the computation tree. It's the tree that you can actually now use for these results. Whereas the left tree, it's not very clear how you would do that, or how would you, like you can have a node, as Michael said, you can just add a node, or label a
I'd
node.
say you just leave it there. You can just leave it there. What the node adds, if you didn't have that node at the top, then that minus operation that is at the top, look at its thread. It wouldn't have a place for the R thread to point to. So by putting in that top node, you've made everything complete. That's all it's there for. It makes the algorithm a little bit simpler.
Yeah, I would agree with that. Yeah. Okay, cool. So we are just a little past 3. Let's take a 10-minute break till about 3:18. And when we return, we'll continue with the differentiation algorithm. And in the meantime, please enjoy your break, refill your coffees, and turn off your camera and mute. The meet obviously will stay up, and the recording will also continue. Okay, we're back. So whenever you get back, if we can just continue the reading, pages 338 through 340. We'll spend about 5 minutes till 3:24 New York time. Okay, what are we trying to do here? What's the problem and how is the tree going to help us?
It's symbolic differentiation of an expression that's represented as a tree.
Okay, Michael, could you just quickly review what differentiation means?
Oh gosh, differentiation. Well,
Oh, just in terms of how Knuth presents it, those.
he presents it strictly algebraically by these rules that he gives. D of x equals 1, D of a equals 0, going on down to the one at number 19, which I don't think I ever learned that one. But that one simplifies for like D of x squared. If you plug that into that rule, you'll get 2x dx.
So the D operator is the result at a particular node. Is that the idea?
Well, you apply the D operator to the entire tree by looking at what the tree represents. Like if you applied it to the tree that we had, what's the first operation is a minus. So you look in the rule for u minus v, and it's going to say that in order to apply differentiation to that root, you're going to apply differentiation to the left and to the right and subtract those two. So that's an easy one. Sometimes you'll have to copy and differentiate. Like if you were multiplying, you'll have to copy the subtrees and differentiate one and multiply it by the other and then add according to that rule.
So you're referring to equation 17.
Equation 17, if you hit if that top node on the tree had been multiplication, you would have to start by making a copy of, you would start by looking at the left branch. I guess no, that wouldn't be a way to say it. You would start by making it's going to be a more complicated tree. You're going to have plus at the top of it. And on the left, you're going to have two subtrees. One is the derivative of the left, and the other is the right, and you're going to multiply them. I can't explain this in words. You have to do it on a blackboard almost.
Well, I think basically what the way I understand it is that because in certain derivative equations, the definitions, you need to, in some sense, construct a new tree, with an operator with additional children, and so that subtree in the original tree will need to be transformed to another tree, and so that may involve more nodes, and so I think that's where the copy is coming from.
Yeah. If you look at, like, for instance, equation 13, which is just the logarithm, so that would be a logarithm plus a tree that might contain 100 nodes. And if you apply the differentiation on that, what's going to happen is you're going to need a tree that has division at the top. On the right branch, which is the dividend, you would have that same tree with 100 nodes, and on the left, you would have you would start off with the same tree, but you got to apply the differentiation operator throughout it. It may end up with only one node, depending on how much simplification it allows.
Does this go back to Gabriel's question about the y? Like, can we see the benefit of that y now? That y node on the binary side?
I can't see the benefit of it. Like I said, the benefit is in the low-level details of the algorithm, where that top node, the algorithm is going to depend on that thread. And that top node, if you didn't have that y, that top thread will point to nothing. There's nothing for it to point to. But when you have it there, if you follow that right thread, you don't have to worry about it pointing to nothing or set up a representation for what that means. You just follow it and you get to that Y. And if you continue following the right link, look at it. It loops on it. It loops in on itself.
Mm-hmm.
Fine. It doesn't mean anything.
Okay. Any other questions or comments?
Like I said before, Knuth prefers infinite loops to null pointer exceptions. That's all I can say.
Okay, do we have a pretty good handle on, at least conceptually, how the tree will be used for the symbolic differentiation? Okay, let's go on to the actual algorithm. It's on page 340. And we'll spend about 5 minutes. This is just the algorithm, the 5 steps of algorithm D. Okay, do we need another minute or two? All right, who can explain what's going on here?
Well, it's bottom-up differentiation. You're going down to the lowest element. But what I don't get in D2, if the first time you hit D2, you're following that tree in well.
So the part I don't still get is the list of symbols is already in post order, or is it like written like in a regular formula?
Oh, it's all. We've already got the tree in post order or in.
So
I mean,
why?
how are we producing the tree in post order or in order?
Miguel, if you're asking about the algebraic representation, then that's just normal algebraic
No,
formula
I'm
representation.
asking about the algorithm, right? So I'm asking if this says if y is the address of the list head that points to the formula represented as described above. The question is that list is the formula, so the tree of the formula in post order already.
Yeah.
All right.
So P is going to be the first element of the tree in post order. And that is, I think that's the 3.
That'll be a 3, yeah.
Okay, so then in D2, when it says set P1 from L link of P, there is no L link of P.
So then it says, and so if P1 is not null, right? So it might not have one.
Yeah, I guess. All right, that must be it. So I guess the thing is the diff function that he's talking about, we don't know what that is. That's something it's going to call. That's going to do the actual differentiation depending on what we found. So for a constant like the 3, it's just going to return a 0.
Yeah, presumably. It's in the next page.
Yeah. Yeah, well, and so we get that 0, and it's not linked anywhere. Where do they put it? I don't know.
So in D2, he says, once you've done the diff operation, then that will set pointer variable q to the address of the root of the derivative.
Right. So that would be for that first node. That's just going to be a 0 because we're differentiating a 3.
Okay.
But what do we do with it? It's going to be important in some cases. Maybe not in this one, but in some cases. Where does that Q go? Oh.
So the Q, I think it's in D4.
Yeah. Set our link of P2.
Yeah.
Set
And what?
P2 from P.
Yeah. What is P2?
It's a copy of P.
Right.
Not a copy of the node. It's isn't that the address?
It's a copy of the pointer. It's a copy of the pointer.
It's a copy of the pointer. It's a copy of the pointer, and we're setting. Well, it's a copy of that structure. I don't know what it is. Isn't it the address of that structure where P is?
Yeah, where the derivative is. So who can explain the parentheses in D4? This is the tricky part of the algorithm. We temporarily destroy the structure of tree Y so that a link to the derivative of P2 is saved for future use. The missing link will be restored later in step D3. So if we continue with, Michael was referring to the example that we're looking at, the y equals 3 times log of x plus 1 minus a over x squared, then maybe somebody can walk us through that. How does the algorithm proceed with that input?
Well, the diff is going to return a node with just a 0 in it. No left subchildren, no right subchildren. All it's got is a 0 in it. But then when you get to, D3 is the next step. If type of P denotes a binary operator, it does not. It's a constant. It's the 3.
Yep.
Now on D4, set P2 from P. So P2 and P are both pointing to the 3. And set P to P dollar, so P dollar goes to the successor, which I think is an X. I'm not sure. I'd have to look back. It's somewhere else, way off down the tree. Now, if our tag of P2 equals 0, that is if node of P2 has a sibling to the right. It doesn't. Mm-hmm. It's just the 3. So it's not even the tricky part of the algorithm.
Yep.
But what happens to it? Where does the Q go? Oh, set our link of P2, but that's only if.
Then we go to step D5.
Step D5. If P does not equal Y, which it doesn't, return to step 2, D2.
Yeah. So I think when you get to the first plus sign, you start to get the operation that uses the trick, right?
What will be the state when we get to that plus sign?
I'm still trying to figure out what happened to that 0.
That's an extremely good question, though. You have the 3, the x, and the 1. So theoretically, you have to store 3 trees for 3x in 1 and 3 trees for their derivatives, which means 0, 1, and 0. So you have at least 6 subtrees when you get to the point of when you get to the plus sign, right?
What happened to the Q? What happened to the Q? I mean, it's eventually the Q is pointing to a 0 node, and if you're doing a simplification, it's going to multiply by something or add to something and just go away. But It looks like when I'm tracing the algorithm, it looks like the algorithm just forgets about it, and it goes to D5 like we said, and P does not equal Y, so it returns to step D2, and then in D2 we get another Q. We overwrite it. But when we get to D2 the second time, that P is now pointing to the X of the X plus 1, or is it 1 of the 1 plus X? Let me look back. The second element in post order, what would that be? It's the X.
Yeah.
So we have at the point that we begin D2, we have this Q pointing to a really simple node that just contains a 0. But we didn't look at the fact that it contains a 0. It could have been anything. Could have been 100 nodes for all we know at this point.
Yeah.
And P is pointing to the X. And then we apply diff on the X. And you know, in this case, a diff of an X, the rule will be to return a 1.
Mm-hmm.
And the same thing happens. What happens to that 1? I'm not doing something right.
Why not?
Because I'm losing the Q, and later on if I do it again, I'm gonna lose the 1.
Wait, why does the Q get lost? Why don't you have two twin subtrees, one pointing to the element and one pointing to the derivative of the element?
In step D5, it seems to me that the Q is being retained. It turns into the left, it's used to set the left link.
That says otherwise set L link of dy from Q. Wait. Yeah. If
Okay.
P does not, wait a minute. If P does not equal Y, return to step 2. P does not equal Y.
Yeah, if P equals Y, we would be done. If P equals Y, we would be done.
Right. So if P does not equal Y, return to step D2. Otherwise, that otherwise is only done at the very end. So what happened to the Q?
Okay, so let's continue, and hopefully things will become a little more clear. So this is the next couple of pages that have the different operators being described.
Okay, wait a minute.
Okay.
Q gets put into R link of P2 in D4 because that's what happens to it. Why did we think that it skipped that? Because that 3 has a right sibling. So now if R tag of P2 equals 0, that is if our node P2, which is a copy of P, has a sibling to the right, then set R link of P2 from Q. And formerly, this is the tricky part of the algorithm because formerly that 3 was just sitting there as a terminal node, and now we're taking that terminal node, the R link would have been the thread, and instead we're jamming in a pointer to this thing that we got back from diff. I guess it's going to fix it up later. Now it makes sense to me.
Okay.
Why did we think we were skipping that before?
Let's read, and we can continue on with this same discussion after the next reading. Okay, so I think one thing that could help is could somebody write out the post order traversal of this algebraic expression tree, just like we did for the tree with the alphabetic nodes. So if you could just write that out, the example that we're looking at, the 3 times log of x plus 1, so on.
If I could find my chat button. That's what it is. We were talking last time about doing the 3 and the x. Did I get that right?
That doesn't look right.
What's wrong with it? Post order, right? That's the order that the algorithm is going to visit it in.
Post order 3.
You got to go to the left node, and then the right node, and then the root.
Right.
What's wrong with that?
So wouldn't it be 3 and then log?
Nope.
3 and then, sorry, x. Yeah, 3 and then all the way down to x.
You got to go all the way down, yeah, and then
and then
you come up to
1,
the you come
and then
the plus, but you got to do the children first. So you
log.
You get the 1, and then now you've got the 3 and the 1, so you've done both the children. So you have the plus next, and then the log is done. The log only has one child, so you do the log is next.
Right.
I think that's right.
Yeah, that's right. Okay, so did this help going through the operators, the description of the operators? Does it help with the algorithm? Or just made it more complicated?
I don't think it helps with the algorithm because we're doing something different here. But towards the end of the discussion last time, I once I figured out what was going on with the queue, now the algorithm is starting to make sense.
Yeah, it does help with the algorithm, I think. Yeah.
So if we look at Michael's response with that post order traversal, so can we do a transformation here and maybe replace some of these things with the big D of something that represents the derivative at some point?
I don't know
some of these nodes.
Yeah. So for the first one, the first time at D2, it's going to be D of 3 is what you're trying to do, which is a 0.
Right.
And my new understanding of that algorithm is you're going to stick that 0 temporarily on the right link of the 3, which violates the structure of the tree, but we're beyond that, and it's going to fix itself up later.
Okay. So at that point, if we did that same traversal, what would it look like?
Where would that be? That would be. It would actually be the first element, D of 3, and then X, and then 1, like that.
Because it becomes the left link.
It's the right link. But it's a child. So the child comes before the root.
Okay. Yeah. That's right. It is the right link, and it's a child. So yeah, D3, and then so on. And
And
then
that's really that. I mean, it isn't a D3 in the diff is going to just return a 0 there, but the 0 came from differentiating the 3. So what if you looked at the algorithm after D3, the tree after D3, which is where it gets linked up, it's going to be a 0x 0 3 x is where the I'm going to put a $sign there. That's where our cursor or what that's where our P is pointing to, and then it follows on 1 plus ln like that.
I think that
but
that
put a
X
$sign there.
Michael, that X there is a times, right?
No, that X is the X. X plus 1.
Oh yeah, right. Yeah, it is the X. It's the variable X.
Yeah. Like I said, you need a blackboard.
Yeah.
So after D3, after the first invocation of D3, this is what the tree looks like, but P is pointing to that X now. And then we're going to do the same thing. We're going to apply diff on the X, so that's going to make a 1. So I guess you'd end up with 0, 3, 1, X. The next element in preorder is the 1. So it's going to look like that. And it gets fixed up it's going to hopefully get fixed up when we do the operators, but I don't know.
So basically, when you get to the plus, and then you apply diff, what number was it?
Go one more time. When you apply diff on the 1, you got this 0, 3, 1, x 0, 1. So now the P is pointing to the plus, and it's got those trees. That doesn't really tell you exactly how the trees look, does it?
It gives you an idea.
Gives you an idea, but that's no, it gives you an idea, but pre-order traversal or post-order traversal of the tree is not homomorphic.
It's not that intuitive. It's not, you have to kind of do this mental mapping, and it would be nice if we did have all the transformations represented as trees, if we could see them. That would be really nice.
Yes. Well, I guess you could put parentheses around it.
Yeah, that's true. That's actually something that we will read in the next section next week. The other kinds of representations for trees. But
you like this, I guess.
Are you familiar with the GraphWiz software?
No, I'm missing a paren here. Yeah, we made one here. I'm going to turn you guys into Lisp programmers reading this. That doesn't help much.
So it occurred to me. I'm sure that you've seen or know about GraphWiz. It's often
I've never
used
heard of it.
for Doxygen, documentation generation, but that would be interesting is to basically generate GraphWiz representations of these trees at each point of the algorithm, and then you could easily look at the visual representation. Yeah, I'll think about that maybe for next week.
The next step is the interesting one because it's going to simplify everything. It's going to simplify
reduction
everything for that x plus 1. When you do apply differentiation to x plus 1, you should just get just an x or just a 1.
Just a 1, yeah, just a 1.
But you need to carry the x up too.
Well, not yet though. Not yet. I think you get the uncompressed representation. So technically, when you apply diff4, which is the differentiation rule for the addition, you add basically a new subtree which has as a root the plus sign, and as the left and right children the expressions for both derivatives, the pointers for q and q1.
You're right. You're right. But look at it closely. If it's a zero on the plus, if it's a zero, it's going to throw it away.
Oh. Yeah. Okay. Yeah. Good point.
You are right. If that was x and y, you are right. The tree would be a plus with the derivatives on it.
Yeah. So the simplification is already built into the differentiation.
Some simplifications are built in. That's yeah.
Yeah.
You catch what we're talking about, everybody? I'm looking. Which one is that? Is that diff 5 or diff 3?
Diff 4, I think, is the addition.
Diff 4 is the addition. So it says. So look at diff 4. It says if info q1 of 0, then avail is your free memory. Set avail from q1. In other words, put q1 back onto free memory. Otherwise, if info q is 0, put q onto free memory.
Yeah. Yeah.
And put q from q1, and then it's going to either return just the q. If one of the terms is 0, it's just going to return the other. And if they're not 0, then it'll return a tree of plus q1 and q.
Yeah,
I feel like at this point we do have an intuitive understanding of how everything works, but perhaps it would be useful to do like a very simple example on the binary tree, like the converted tree, just to see where each node goes. But I do think we understand what's going on at this point, basically.
That's great. So Michael did bring up the avail notation or the syntax, and avail just refers to the free memory or the heap. And so when you have an arrow to the left going towards avail, that means you're freeing memory. And if you have an arrow going from avail to some symbol like Q or P, that means you're allocating a node.
Yeah.
So
I think of that double arrow as meaning a stack. I think somebody told me that a couple of times ago. So it means push Q onto avail.
Yeah, sure. Yeah, so there's not a lot of notation, but yeah, whatever there is, it's very idiosyncratic and special to Knuth and TAOCP, so it can throw you off a little bit. But once you know, then there's not a lot. So yeah, any other comments? I don't think we'll have time to go through the code today. We'll see if we want to pick it up next time.
It's already 4:04.
I'm sorry?
It's already 4:04. My time flies when you're having fun.
Yeah, exactly. So, or, some things that I've done in the past is, I'll record like a separate thing just on the code and step through that. So if I have time, I'll try that. But I think what would be nice is I'll look into generating the graphs, the trees for each one of these steps.
Yeah, that would help. I think it would be about 100 steps to differentiate that polynomial. But if you carried it through to the first operation, maybe the second operation, the first operation is only a plus, and it's too simple. The logarithm, though, is kind of interesting a little bit. And it's not as complicated as x divided by y would be.
Yeah.
So if you could carry each step, that would be good.
Yeah. Yeah, that's a nice idea. Okay, so so I think we will call it a day, and I think we may pick this up.
Last week we had that induction problem.
Remember
this?
Which one?
It was proving that 2 to the x or 2 to the nth is greater than n cubed if n is greater than n is greater than 10. and I solved it.
Okay.
If anyone's interested, I can go through it. It's kind of clever.
Yeah, please do. So could you refer us to the page?
Oh, the page. It was in induction. It was near the top, but I'll just write it in. You were supposed to prove 2 to the nth is greater than n cubed.
Michael, was that one of the actual exercises or just something
No,
that...
it wasn't. No, it wasn't. It was in the text.
Oh, yeah, I see it. I see it. I'll type it in. I'll type it in.
Yeah. So what we needed to prove by induction, so we know that 2 to the nth is greater than n cubed. So what we wanted to prove would be 2 to the n plus 1 is greater than n plus 1 cubed. I wish I had a blackboard because it would work a lot better. So 2 to the n plus 1 is 2 to the nth plus 2 to the nth. And
Yep.
we know that that is greater than n cubed plus n cubed. Like that, right? So 2 to the nth. So I'm going for that first line, 2 to the n plus 1. I know from my induction that 2 to the nth is greater than n cubed. So if I add 2 of them...
Sorry, Michael. Michael, is that the left-hand side? Left-hand side.
Supposed to be plus.
That should be 2 to the n times...
2 to the n plus 1 is equal to 2 to the nth plus 2
plus
to the
2
nth.
to the n. Okay, yeah, got it.
Right.
Yep.
And n plus... and we know from the induction hypothesis that each of those 2 to the nth is bigger than n cubed. There should be a plus between those two. So you with me there? So we know this part. We got to get to the first line that I wrote there. So we could rewrite this. This is... This is what I call pulling a rabbit out of a hat. Mm-hmm. Why would you do that? So the n cubed, the second n cubed, is bigger than 7 times n squared because n is greater than 10. So you see that? In other words, I've only made it smaller by making it 7 times n squared instead of n cubed. And I'm calling it pull a rabbit out of the hat because you're thinking, why did I use 7?
Mm-hmm.
Maybe you already know. Okay?
Well, I think that you're going to factorize it.
Yeah. So the 7n squared becomes 3n squared, and then another 3n squared is greater than 3n, and an n squared is greater than 1. And there you go. There you have it. That's 2 to the n plus 1 is greater than n plus 1 cubed.
Okay. Very nice.
The interesting part is pulling that 7 out. Or could it? The bit 7 being, n plus 1 cubed is n cubed plus 3n squared plus 3n plus 1. Anyway, I got a kick out of it when I discovered it or when I figured it out.
That's great. Just for the benefit of the others, we reviewed, or we actually covered this section last week because we started trees about 2 or 3 weeks ago, and we noticed that induction was being used in a number of places to prove properties of trees because they're sort of this recursively defined structure. And the way we've been proceeding is not, sequentially through the text. We have been jumping back and forth, trying to get as much of the data structures and algorithms before we actually go to some mathematical preliminary that may be needed or not. So when we come across something, then we cover that stuff. And induction had not really come up before, so that's why we covered it last week. And hopefully that's the way we'll continue. So we've skipped a lot of the preliminary sections, but whenever they come up, we'll cover them.
Yeah, none of what I said will make any sense if you don't know what induction means. I didn't really explain that. So I think probably most people would know what induction is. Maybe. Am I wrong? I think probably.
I think it's fair to say, because I think induction, like the basic induction hypothesis, is really part of high school curriculum. So I would think at some point everyone has been exposed. But I would also strongly recommend that even if you think you know induction pretty well and use it, still look at this section, because Knuth presents it in a different way. It's a very constructive way and very interesting way. So, but again, until we need it, until we start to use it in some algorithm or data structure, we generally have not covered it. So there'll be ample opportunity for anyone who joins up later to catch up on that stuff, because we've skipped a lot of the preliminaries. Okay, great. Well, thanks a lot, guys, for attending. Really happy to see some new attendees. I hope you can make it regularly if it's convenient for you. But in any case, please follow along and watch the videos. And if you have anything that you would like to cover, in terms of the text, be sure to let me know, and we'll definitely take that into account. All right, bye-bye.
Thank you, Sakai.
Yeah, thanks, Michael.
Thank you. You're hosting this. You're doing all the work, and we're getting all the entertainment.
No, the work is done in the session, right? I have barely read this in advance. So I'm really benefiting from the discussion as well.
Awesome.
Bye-bye.
Yeah, thanks again. That was a good session.
All right.
Cool. See you guys.
Yeah.